observe as something quiet has been moving through our sky long before anyone thought to look for it. You didn't arrive here by accident. A distant motion, subtle and patient, has drawn this moment toward you. What if an object born around another star crossed billions of years of darkness, only to pass through our solar system once on a path so precise it should almost never exist? What if the James Webb Space Telescope caught its light not as a blur but as a chemical signature that does not belong to us? A narrow shape glides through the cold, indifferent space beyond Mars. No sound, no warning, only data drifting toward meaning. A visitor that does not slow, a story that does not repeat. Stay with me. The discovery of 3 Atlas was not the result of chance curiosity or speculative searching, but of a disciplined routine. Astronomers rely on automated survey systems that repeatedly scan the sky, night after night, comparing new images against older ones to detect motion. These systems exist primarily for planetary defense, built to identify asteroids that might one day approach Earth too closely. Most detections are unremarkable, following well-mapped orbits shaped by the Sun's gravity. Yet within this vast stream of expected data, a single object began to stand apart. Its motion did not match anything familiar. Against the fixed background of distant stars, it moved quickly and along a path that refused to curve into a closed orbit. As additional observations accumulated, the anomaly became undeniable. This object was not bound to the Sun. Its trajectory was hyperbolic, meaning it would pass through the solar system only once, before continuing outward into interstellar space. Gravity would bend its path but never capture it. The conclusion was unavoidable. This object came from beyond the solar system. The designation 3 Eyes Atlas captured both its identity and its significance. The letter I signified an interstellar origin, confirming that the object was born around another star. The number 3 placed it among a very small and exclusive group. Only 2 such objects had ever been confirmed before. The name Atlas acknowledged the survey system that first detected it, quietly marking a milestone in modern astronomy. With that designation, the object was formally recognized as the 3rd known interstellar visitor to pass through our cosmic neighborhood. The rarity of this classification carried weight. The first confirmed interstellar object detected in 2017 challenged scientific expectations with its unusual shape and lack of visible cometary activity. The second, discovered in 2019, appeared more familiar, surrounded by gas and dust, yet revealed chemical differences that distinguished it from comets native to the solar system. Each encounter forced astronomers to expand their assumptions. The arrival of a 3rd object suggested that these visitors were not singular oddities but representatives of a larger population drifting unseen between the stars. What made 3I Atlas especially compelling was its speed. Moving at hundreds of thousands of kilometers per hour, it travelled far too quickly to be gravitationally bound to the Sun. This velocity implied a long and complex history. Objects do not achieve such speeds without powerful interactions such as gravitational encounters with massive planets or stars. The path of 3 Atlas hinted at a violent ejection from its original system, likely during the chaotic early stages of planetary formation. This single passage through the solar system imposed strict limits on observation. Unlike periodic comets, which return again and again on predictable schedules, an interstellar object offers no second opportunity. Every measurement must be taken during its brief visit. Once it leaves, it will fade into darkness, perhaps never to be observed again by any civilization. This fleeting nature transformed the discovery into a race against time, not driven by urgency or fear, but by the recognition of rarity. Scientific interest intensified as telescopes across the world turned toward the object. Each instrument offered a different perspective. Visible light observations tracked its motion and brightness. Infrared measurements probed the heat signatures of escaping gases. Spectroscopic analysis began to reveal its chemical makeup, allowing scientists to compare it with known comets and asteroids. These observations were not about spectacle, but about reconstruction. From light alone, researchers attempted to infer an origin story billions of years old. The importance of such an object lies in what it represents. Interstellar bodies are fragments of other planetary systems preserved through immense spans of time. They carry material shaped under conditions that may differ radically from those that form the Sun and its planets. Radiation, cosmic dust, and thermal extremes sculpt them slowly as they drift through the galaxy. Their interiors can remain largely unchanged, acting as natural archives of ancient chemistry. In this sense, 3I Atlas is not merely an object of motion, but of memory. Its composition provides clues about the environment in which it formed, including temperature, chemical abundance, and the structure of its parent disk. Differences between its materials and those found in solar system comets offer insight into how varied planetary systems can be. They challenge the idea that the Sun's neighbourhood represents a universal template. The discovery also carries broader implications for understanding the galaxy itself. If interstellar objects pass through the solar system with any regularity, then the space between stars is not empty, but populated by debris from countless systems. These fragments are the byproducts of planetary formation, migration, and destruction. Their existence points to a dynamic galaxy where systems constantly exchange material, even if such exchanges are rarely noticed. Historically, astronomy progressed by observing distant light and inferring unseen structures. Interstellar objects reverse this pattern. They bring distant material directly into reach, allowing physical sampling without leaving the solar system. This shift represents a quiet transformation in observational science. Instead of studying other systems only through telescopes aimed across light years, researchers can analyze actual remnants from those systems as they pass by. Yet the discovery of 3I Atlas also reinforces scientific humility. Each new interstellar visitor has complicated existing models rather than confirming them. The data often resist simple explanations. This is not a failure of science, but its natural state. Knowledge advances through refinement, contradiction, and revision. Objects like 3I Atlas remind researchers that certainty is provisional, and that the universe does not conform to human expectations. Ultimately, the significance of 3I Atlas lies not in drama but in perspective. Its passage is a brief intersection of paths in a galaxy defined by vast distances and deep time. It neither threatens nor announces itself. It simply moves governed by physics older than humanity. By observing it, scientists gain insight not only into another star system, but into the processes that shape all systems, including our own. When 3I Atlas departs, it will leave behind only data calculations and refined questions. The object itself will continue its journey carrying no record of the attention it briefly received. Yet its influence will remain quietly reshaping theories of planetary formation, galactic exchange, and cosmic diversity. In that way, its brief visit becomes part of a much larger scientific narrative, one that stretches far beyond the moment of discovery and deep into the history of the universe. The recognition of 3 Atlas as an interstellar object immediately shifted scientific focus from detection to interpretation. Identifying an unusual trajectory is only the beginning. Understanding what such an object truly represents requires careful measurement, comparison, and restraint. Every assumption must be tested against data because interstellar visitors do not share the evolutionary history of bodies formed around the Sun. The first task was to confirm its motion with precision. Astronomers tracked 3I Atlas night after night, refining calculations of its orbit. The results were consistent and unambiguous. Its path was hyperbolic, not elliptical. This alone placed it outside the solar system's gravitational family. Objects born near the Sun follow closed orbits, returning again and again unless disturbed. 3. Atlas did not. Its trajectory revealed a path shaped elsewhere and a future that would never intersect our system again. Speed provided a second critical clue. Travelling at more than 200,000 km per hour, the object exceeded velocities typical of solar system comets. Such speed cannot arise randomly. It suggests a history of strong gravitational interactions likely involving massive planets or close stellar encounters. During the early stages of planetary systems, large bodies migrate, collide, and scatter smaller material outward. 3I Atlas appears to be one of these survivors expelled with enough energy to escape its birth star entirely. This realization reframes the object as evidence of chaos rather than anomaly. Planetary systems are not static architectures. They evolve violently before settling into stability. For every planet that remains, countless smaller bodies are displaced or destroyed. Interstellar objects are the remnants of this process, carrying the imprint of those early disruptions. Their existence implies that ejection is not rare, but a natural consequence of planetary formation. With motion-confirmed attention turned to physical properties. Measuring size is difficult when an object is surrounded by gas and dust. The solid nucleus remains hidden within a glowing envelope, making direct observation impossible. Scientists rely instead on indirect methods analysing brightness gas production and thermal behaviour. These estimates suggested that Thrusia Aya Atlas is several kilometres across, comparable to a small mountain or city. Even this range carried uncertainty, reflecting the limits of observation at such distances. Mass estimates added another layer of intrigue. Calculations based on size and activity implied a body far heavier than many known comets. If correct, this would indicate an unusually dense structure. Most solar system comets are porous, fragile conglomerates of ice and dust. A denser composition suggests either a different formation environment or a long history of compaction and erosion. Either possibility points again to a foreign origin shaped by unfamiliar conditions. The object's behaviour complicated matters further. Active comets typically exhibit non-gravitational acceleration. As ice turns to gas and escapes, it acts like a series of tiny thrusters subtly altering the comet's path. This effect is well documented and expected. Yet 3 Atlas showed little evidence of such deviation. Despite releasing significant amounts of gas, its motion remained almost perfectly aligned with predictions based on gravity alone. This contradiction challenged standard models. One explanation is extreme mass. If the object is heavy enough, the force from escaping gas may be insufficient to alter its trajectory noticeably. Another possibility lies in symmetry. If gas escapes evenly across the surface, the forces cancel each other out, producing no net push. A third explanation involves internal structure, suggesting a rigid or unusually strong nucleus that resists deformation and uneven venting. Each hypothesis carries implications beyond this single object. A dense interstellar comet would expand the known range of cometary types. A uniformly active surface would imply internal porosity, unlike that seen in solar system counterparts. A structurally strong nucleus would challenge long-standing assumptions about comet fragility. In every case, 3I Atlas appeared to occupy unfamiliar territory. Chemical analysis deepened this sense of difference. Spectroscopic observations revealed a composition dominated not by water vapour, but by carbon dioxide. In solar system comets, water ice is the primary driver of activity near the Sun. Carbon dioxide is present, but usually as a secondary component. In 3I Atlas, this balance was reversed. The ratio was among the most extreme ever observed. This chemical signature carries profound meaning. The abundance of carbon dioxide suggests formation in a much colder or chemically distinct region of a protoplanetary disk. Ice lines the distances from a star where specific compounds freeze, shape what materials become available to form planets and comets. A system dominated by carbon dioxide ice would produce objects fundamentally different from those formed near the Sun's water-rich frost line. Such differences ripple outward into planetary development. Comets are thought to deliver volatile compounds to young planets, influencing atmospheres and surface chemistry. A system seeded by carbon dioxide-rich bodies would evolve differently from one shaped by water-rich impacts. In this way, 3I Atlas becomes more than a curiosity. It is a data point in understanding how diverse planetary systems may be across the galaxy. Traces of additional substances complicated the picture further. Observations suggested the presence of metals such as nickel, a material associated with high-temperature environments. This combination of cold chemistry and heat-resistant components hints at a turbulent origin, suggests mixing between inner and outer regions of a forming system driven by migration shocks or stellar activity. Such mixing aligns with modern models that depict planetary formation as dynamic and chaotic rather than orderly. Age estimates extended the object's significance into deep time. Based on velocity and trajectory, scientists inferred that 3I Atlas may be billions of years old, possibly older than the Sun itself. If accurate, it represents material from an earlier generation of stars carrying a chemical record of the galaxy's past. Over such timescales, the Milky Way's composition evolves enriched by successive stellar deaths. An object this old offers a rare sample from that earlier era. Survival over such a duration is remarkable. Interstellar space is hostile. Cosmic rays bombard surfaces, altering chemistry. Micrometeorites erode outer layers slowly but relentlessly. Thermal cycling during close stellar passes stresses internal structure. That 3i Atlas remains intact and active suggests resilient size and perhaps protective layering formed over eons. Taken together, these observations transform 3i gas Telus into a historical artifact rather than a transient event. It embodies processes that occur far beyond observation preserved through time and motion. Each measurement adds context not only to this object, but to the broader understanding of how systems form, evolve and exchange material. As analysis continues, certainty remains elusive. The object resists simple classification existing at the boundaries of known categories. This resistance is not a problem to be solved, but a signal to refine perspective. Interstellar objects like 3i Atlas reveal that the universe is more varied than any single model can capture. Their value lies precisely in their ability to unsettle assumptions and expand the scope of inquiry. As observations of 3i Atlas continued, the focus gradually shifted from what the object was doing to what it could reveal about where it came from. Motion and chemistry tell only part of the story. To understand an interstellar visitor, fully scientists must place it within a broader cosmic timeline, tracing its journey not only through space but through history and measured in billions of years. Age estimates for 3i Atlas are necessarily indirect, yet they are grounded in well-established physical reasoning. Its extreme velocity suggests that it has been travelling through the galaxy for a very long time. Objects ejected recently from nearby systems would tend to retain speeds closer to those of their parent stars. The unusually high speed of 3i Atlas implies repeated gravitational encounters over vast timescales, each interaction subtly altering its trajectory and adding energy to its motion. These encounters act like cosmic slingshots. As an object passes near a star or dense molecular cloud, gravity can transfer energy, accelerating it without any physical contact. Over billions of years, even rare encounters accumulate. The result is a body moving faster than most stars in its region of the galaxy. This dynamic history places 3i Atlas among the oldest known travellers, potentially originating from an era when the Milky Way itself was far younger. If the object is indeed several billion years old, it likely formed around an early generation star. At that time, the galaxy contained fewer heavy elements. Stars forged those elements through nuclear fusion and scattered them through supernova explosions. Each successive generation of stars inherited a richer chemical environment. The composition of 3i Atlas may therefore reflect conditions that no longer exist in modern star-forming regions. This possibility elevates the object from a mere curiosity to a galactic fossil. Its chemical makeup becomes a record of ancient environments preserved through immense spans of time. Unlike planets which undergo geological change, or stars which evolve rapidly on cosmic scales, a small interstellar body can remain chemically stable for billions of years. It carries within it a snapshot of the materials available during its formation. Survival over such timescales requires extraordinary resilience. Interstellar space is not empty. Cosmic rays constantly bombard exposed surfaces, breaking molecular bonds and altering chemistry. Over millions of years, this radiation can darken surfaces and create complex organic residues. Micrometeorite impacts gradually erode outer layers, removing material atom by atom. Thermal cycling during close stellar passes introduces stress that can fracture weaker objects. That 3i Atlas remains intact suggests a combination of size, strength, and protective layering. Models indicate that prolonged exposure to radiation can create a hardened outer crust composed of complex carbon-rich compounds. This crust may act as a shield, preserving pristine material beneath. When the object enters a new stellar system and warms, this ancient shell can fracture, releasing gases that have remained trapped since formation. This process offers insight into the internal structure of interstellar objects. Rather than being loose aggregates, they may possess layered compositions shaped by time and exposure. The release of gas across much of the sunlit surface of 3I Atlas supports this idea. Instead of isolated jets, activity appears widespread, suggesting internal porosity and channels that distribute heat efficiently. The implications extend beyond comet science. Interstellar objects provide evidence that planetary debris can survive long after its parent system has evolved, or even ceased to exist. Stars move, systems disperse, and yet their remnants continue drifting through the galaxy. In this sense, 3I Atlas is not only a visitor from another place, but from another epoch. Its journey also reflects the dynamic nature of the Milky Way. Over billions of years, stars orbit the galactic center, spiral arms shift, and molecular clouds collapse and dissipate. An object like 3I Atlas may have crossed multiple spiral arms, passed near regions of intense star formation, and endured environments far harsher than the outskirts of the solar system. Each region left subtle marks on its surface and motion. Understanding this journey requires collaboration across disciplines. Astronomers model galactic dynamics to trace possible paths. Chemists interpret spectral signatures to infer formation conditions. Physicists analyze radiation effects and thermal processes. Together, these perspectives transform scattered data points into a coherent narrative, though uncertainty remains an integral part of the process. The presence of 3I Atlas also reframes the search for other interstellar objects. If such bodies can survive for billions of years, then the galaxy may contain vast numbers of them. Most go undetected, too small or too distant to observe. Only when one passes close enough to a star and becomes active does it briefly announce itself. Each detection therefore represents not rarity, but opportunity. This realization influences how astronomers design future surveys. Improved sensitivity and wider coverage increase the chances of detection. Each new object adds statistical weight, allowing patterns to emerge. Over time, a population study becomes possible, revealing typical sizes, compositions, and velocities. From that, scientists can infer how common different formation environments are across the galaxy. Yet even with expanding data, the story remains incomplete. Interstellar objects challenge the assumption that the solar system provides a representative sample of planetary debris. Instead, they suggest diversity as the rule, rather than the exception. Systems may form with different dominant ices, different dust compositions, and different dynamical histories. The Sun's system is simply one outcome among many. There is also a philosophical dimension to this realization. Objects like 3I Atlas remind observers that human history occupies an almost negligible fraction of cosmic time. While civilizations rise and fall, interstellar debris continues its slow passage indifferent to observation. The universe preserves its history not in written records, but in matter and motion. As 3I Atlas moves close to the Sun, it faces increasing thermal stress. The coming weeks will test its structural integrity. Some interstellar objects may fragment under such conditions, revealing fresh material before dissolving entirely. Others may endure shedding layers and continuing onward. Whatever the outcome, it will add another chapter to the object's long history. Eventually, 3I Atlas will leave the solar system carrying with it the imprint of its brief encounter. It will continue through interstellar space, perhaps altered, perhaps diminished, but still moving. For science, what remains will be data models and refined questions. For perspective, what remains is a reminder that the galaxy is not static, and that history moves through it, quietly embodied in travellers that cross our path only once. In studying such objects, astronomers confront both knowledge and limitation. Each answer opens further uncertainty. This balance is not a weakness, but the essence of inquiry. Interstellar visitors like 3I Atlas do not resolve the mysteries of planetary formation. They deepen them, revealing complexity where simplicity once seemed sufficient. As 3I Atlas continued its passage through the inner solar system, attention increasingly turned toward the moment of greatest transformation, its interaction with the Sun. For any small body, proximity to a star represents both opportunity and risk. Heat reveals composition, but it also threatens survival. In the case of an interstellar object, this phase is especially important because it offers the clearest window into material that has remained sealed for billions of years. The Sun is not a passive light source. Its radiation carries energy capable of altering matter at every scale. As 3 Atlas approached, temperatures on its surface began to rise steadily. Ices that had remained frozen through eons of interstellar cold started to destabilize. This process does not occur all at once. Different substances respond to heat at different thresholds, turning solid directly into gas and escaping into space. Carbon dioxide was the first dominant signal. Its abundance explained why the object became active while still far from the Sun, at distances where water ice normally remained stable. This behaviour reinforced the idea that the internal chemistry of 3A Atlas differs fundamentally from that of typical solar system comets. Activity was not driven by familiar processes but by a colder, more volatile foundation. As heating intensified, scientists watched carefully for change. Each new molecule detected would act as a layer peeled back, exposing deeper material. Methane, ammonia, or other volatiles could appear, offering insight into internal stratification. This gradual unveiling resembles geological excavation, except it is driven by radiation rather than tools. The Sun becomes an instrument, forcing ancient matter to speak. Yet this illumination comes with uncertainty. Increased gas release places mechanical stress on the nucleus. Internal pressure can build. Cracks may widen. In some cases, comets fracture, entirely breaking into multiple pieces. Such events are not rare among first-time visitors to the inner solar system. Objects that have never experienced intense heating often lack the structural adaptation needed to survive it. For 3 Atlas, the risk was amplified by timing. Its closest approach to the Sun occurred during a period when Earth-based observation was severely limited. As the object moved behind the Sun from our vantage point, it entered a region of glare where optical instruments could not follow. This alignment, known as solar conjunction, effectively concealed the most dramatic phase of its evolution. This loss of visibility is a familiar frustration in observational astronomy. Critical moments often occur when conditions are least favourable. In this case, the period of greatest heating coincided with near-total observational blindness. Scientists were forced to accept that the object's most intense transformation might go unobserved. However, astronomy rarely relies on a single perspective. While Earth-based telescopes were blocked, spacecraft orbiting the Sun offered alternative angles. Instruments such as solar observatories and probes closer to the Sun could potentially detect emissions indirectly through changes in radiation, plasma interactions, or radio signatures. These observations, though limited, provided partial continuity. The importance of earlier data became clear. Observations gathered before conjunction served as a baseline, a record of the object's state, before its encounter with maximum solar stress. Chemical ratios, gas production rates, and dust behaviour were carefully documented. When the object eventually emerged from behind the Sun, comparisons could reveal what had changed. This before and after approach is common in planetary science. It mirrors medical imaging, where scans taken before and after treatment reveal internal effects. In the case of 3I Atlas, the Sun itself acted as the intervention. The outcome would reveal how an ancient interstellar body responds to conditions it may not have experienced since its formation. When visibility returned, the questions were straightforward but profound. Did the object remain intact? Had its activity increased or diminished? Were new chemical signatures present? Each answer would constrain models of internal structure and resilience. A surviving nucleus would suggest strength and adaptability. Fragmentation would indicate fragility, perhaps revealing layered composition. Regardless of outcome, the encounter held significance beyond this single object. It tested assumptions about how interstellar material behaves under stellar radiation. Solar system comets have been studied extensively, but they represent a narrow sample shaped by one star's environment. An interstellar object expands that sample, offering a comparative case shaped elsewhere. The possibility of fragmentation also carries scientific value. Fresh surfaces expose pristine material less altered by cosmic rays and interstellar erosion. Such material provides clearer chemical signals closer to original formation conditions. While fragmentation ends the coherent journey of the object, it multiplies opportunities for analysis. At a broader scale, the solar encounter highlights a recurring theme in cosmic history. Stars are both creators and destroyers. They enable chemical complexity, yet they also impose limits. Small bodies orbiting or passing near stars undergo constant negotiation between stability and change. 3 Atlas entered this negotiation late in its existence, long after its birth system had moved on. The episode also underscores the asymmetry between human timescales and cosmic processes. For scientists, the window of observation spans months. For the object, the passage near the Sun represents an instant within a journey lasting billions of years. Heat rises and falls, material escapes. Then cold returns and motion continues. Even if 3I Atlas were to lose substantial mass, its identity would not be erased. What remains would continue travelling altered but persistent. In this way, the Sun's influence becomes a chapter, not an ending. The object's history stretches both before and after its brief illumination. There is also restraint in this understanding. Not every question must be answered fully. Some phases pass unseen. Some processes remain inferred rather than observed. This incompleteness is not failure, but context. Astronomy operates at the boundary between access and distance, assembling narratives from fragments. As data from before and after conjunction are compared, models will sharpen. Gas ratios may shift dust production, may change rotation rates, may alter. Each change offers insight into internal response, yet the core reality remains unchanged. 3I Atlas is a transient participant in the solar system's story. Its encounter with the Sun does not mark its significance alone. Instead, it reveals how stars interact with material shaped elsewhere, highlighting both universality and difference in physical laws. Gravity, radiation, and thermodynamics apply everywhere, yet outcomes vary with composition and history. In the end, the solar passage of 3I Atlas reinforces a quiet truth. The universe reveals itself through interaction. Objects remain silent until conditions force transformation. When that happens, information is released briefly, then lost again to distance. What scientists gather during such moments is never complete, but it's enough to refine understanding. The Sun illuminated a traveller from another system not to welcome it, but to expose its nature. Once that light fades, motion resumes and the object returns to the long silence between stars. As the immediate drama of solar heating passed, attention shifted towards synthesis. Individual observations taken in isolation reveal only fragments. Meaning emerges when those fragments are placed together, compared and tested against one another. In the case of 3I Atlas, this process required an unusual level of coordination, drawing on instruments across Earth and space, each contributing a different layer of evidence. No single telescope can capture the full nature of an interstellar object. Visible light observatories track dust and shape infrared instruments, probe heat and molecular emissions. Ultraviolet sensors reveal photochemical processes, and radio facilities search for faint signals that bypass glare. Together, these perspectives create a composite view not unlike assembling a geological cross-section from a scattered cores. Space-based observatories played a central role. Freed from the atmospheric interference, they provided stable measurements across wavelengths inaccessible from the ground. Infrared data revealed the dominant gases driving activity, confirming that carbon dioxide played a primary role, while water appeared as a secondary contributor. Ultraviolet observations detected the breakdown products of water, offering confirmation of its presence even when direct detection was difficult. Ground-based telescopes supplied continuity. Their flexibility allowed frequent monitoring over long periods, capturing changes in brightness, dust production, and tail structure as the object approached and receded from the Sun. This steady coverage was essential for placing detailed space-based snapshots into context. Without it, isolated measurements would lack temporal meaning. One of the most valuable contributions came from archival data. Once 3I Atlas was identified, astronomers searched older survey images for earlier unnoticed detections. These pre-discovery observations extended the timeline backward, refining orbital calculations and revealing the object's behaviour when it was colder and less active. Such retrospective analysis is a powerful tool transforming past data into new insight. This extended timeline confirmed the object's interstellar origin with greater certainty. The refined orbit ruled out alternative explanations such as long-period solar system comets. It also clarified how activity evolved, with changing solar distance strengthening models of volatile-driven behaviour. Each additional data point reduced uncertainty, even as it revealed new complexity. Polarimetric studies added another dimension. By analysing how light scattered from dust grains, scientists inferred properties such as size, texture, and composition. The results suggested that the dust of 3I Atlas differed from that of typical solar system comets. Particles appeared unusually fine or structured, scattering light in unexpected ways. This finding aligned with chemical evidence, pointing to a distinct formation environment. These physical differences reinforce a broader conclusion. Interstellar objects are not simply solar system bodies displaced elsewhere. They are products of different conditions shaped by different temperature gradients, chemical abundances, and dynamical histories. Their study requires models flexible enough to accommodate that diversity. As analysis deepened, questions of preservation and alteration became central. Which features reflected original formation, and which resulted from long exposure to interstellar space, cosmic rays, micrometeorite impacts, and thermal cycling all leave signatures. Disentangling these effects requires comparison with laboratory experiments and theoretical simulations linking observation to fundamental physics. One recurring theme was resilience. Despite billions of years of exposure, 3I Atlas retained volatile material capable of driving substantial activity. This suggests that interstellar objects can preserve internal reservoirs far longer than once assumed. Protective crusts formed through radiation processing may play a key role in this preservation, shielding interiors until a new stellar encounter triggers release. Such resilience has implications for planetary science beyond comets. It suggests that material exchange between star systems could deliver complex molecules over galactic distances. While the probability of direct delivery to habitable worlds remains uncertain, the mechanism itself is no longer speculative. Interstellar objects demonstrate that transfer is physically possible. The collaborative nature of the investigation also illustrates how modern astronomy operates. Large questions demand distributed effort. Observatories across continents and orbits shared data, rapidly refining interpretations in near real time. This openness accelerated progress and reduced duplication, allowing multiple hypotheses to be tested simultaneously. At the same time, the process highlighted the limits of observation. Certain phases of the object's evolution occurred out of view. Some properties remain constrained only within ranges. Models depend on assumptions that may shift with future data. These limitations are not weaknesses, but boundaries that define the current state of knowledge. In this context, 3I Atlas serves as both subject and catalyst. It drives refinement of detection techniques, motivates development of rapid response observation protocols, and informs the design of future surveys. Each interstellar visitor reshapes preparedness for the next, building cumulative capability. Looking ahead, the goal is not to resolve every mystery posed by 3I Atlas, but to place it within a growing framework. As more interstellar objects are detected, patterns will emerge. Differences will become meaningful only in relation to a broader sample. One object suggests possibility. Many establish structure. The study also carries a quieter lesson. Scientific progress often unfolds through patience rather than revelation. There is no single moment of complete understanding, only gradual convergence. Data accumulates, interpretations evolve, and uncertainty narrows without disappearing entirely. When attention eventually shifts away from 3I Atlas, its influence will persist. Papers will be written, models adjusted, and new questions framed. The object itself will continue onward, altered by its passage, but indifferent to the analysis it inspired. In that sense, the legacy of 3I Atlas lies less in its physical presence than in the perspective it reinforces. The solar system is not an isolated stage, but part of a larger galactic environment marked by exchange and motion. Interstellar objects are reminders that history moves through space, quietly leaving traces that science can read only briefly. What remains after observation ends is not closure, but context. 3I Atlas becomes one chapter in an expanding narrative about how matter travels, survives, and transforms across the galaxy. Each chapter adds depth, not finality, to understanding. As the immediate observations of 3I Atlas settled into data archives and analytical models, its broader implications began to take clearer shape. Beyond chemistry, motion and survival, the object forced a reassessment of scale. Not size alone, but scale in time, in probability, and in humanity's place within a constantly moving galaxy. For decades, interstellar objects were theoretical expectations rather than observational realities. Models of planetary formation predicted that countless fragments should be ejected from developing star systems, yet the absence of detections left uncertainty. The confirmation of a third interstellar visitor altered that balance. It suggested that these objects are not rare but merely elusive. Detection depends less on existence and more on timing sensitivity and observational reach. This realization reframes probability. If 3 interstellar objects have been identified within a short observational window, then the galaxy may contain an enormous population of such wanderers. Most drift unseen, cold and inactive, revealing themselves only briefly when passing close to a star. The solar system moving through the Milky Way inevitably intersects some of these paths. Each encounter is a coincidence shaped by motion on a galactic scale. From this perspective, 3i Atlas is not exceptional because it exists, but because it was noticed. Its discovery reflects technological maturity rather than cosmic novelty. Survey systems now operate continuously, comparing vast quantities of data with precision unimaginable only decades ago. What was once invisible has become marginally detectable. This shift marks a transition in astronomy from static cataloguing to dynamic monitoring. The object also highlights the asymmetry between human and cosmic timescales. A few months of observation represent a negligible fraction of its existence. While researchers track changes day by day, the object itself continues a journey measured in billions of years. This disparity challenges intuition. It reminds observers that even dramatic changes near the Sun are fleeting interruptions within a far longer narrative. The fragility of interpretation becomes apparent here. Conclusions drawn from short observation windows must be framed cautiously. Properties inferred today may reflect transient states rather than enduring characteristics. Activity levels, surface composition, and structural behavior can change rapidly under stellar heating. Understanding requires separating intrinsic traits from momentary responses. This distinction matters because interstellar objects are often treated as representatives of their origin systems. Yet each one carries a unique history of ejection, travel, and alteration. No two will be identical. Their value lies not in uniformity but in contrast. Diversity rather than pattern repetition may become the defining feature of interstellar populations. In this sense, 3i Atlas encourages humility. It resists neat classification occupying boundaries between comet, asteroid, and something else entirely. Such resistance is instructive. It reveals how categories, while useful, can obscure complexity. Nature does not conform to human labels. Instead, it presents continua shaped by circumstance. The object's ancient age deepens this lesson. If 3i Atlas formed before the Sun, then it predates Earth, oceans, and atmosphere. It existed while heavy elements were still being distributed through the galaxy. Its material reflects conditions no longer common, preserved not by intention, but by distance and isolation. In studying it, scientists are not merely observing another system, but sampling an earlier phase of galactic evolution. This temporal reach extends the scope of planetary science into galactic archaeology. Interstellar objects become artifacts carrying records of environments that cannot be observed directly. They complement stellar spectroscopy and theoretical modelling, offering physical evidence of how chemistry and structure varied across time and space. The implications reach even further. Planetary systems are often discussed in isolation, each treated as a self-contained architecture. Interstellar objects reveal that systems leak. Material escapes, travels, and occasionally intersects with others. Over cosmic timescales, this exchange contributes to galactic mixing, distributing fragments of one system into the environments of others. Such mixing does not imply biological transfer, but it does establish physical connection. Molecules formed around one star can travel vast distances, altered but recognizable. This reality expands the conceptual boundaries of planetary science, linking it more closely with galactic dynamics and chemical evolution. The presence of 3i Atlas also influences future strategy. Astronomers now anticipate additional interstellar detections. Survey sensitivity will improve, response protocols will refine. Telescopes will be allocated more rapidly, and analysis pipelines will become more automated. Each new detection will benefit from lessons learned here, yet anticipation must remain measured. Not every interstellar object will be cooperative. Some may pass too quickly, others may remain inactive, revealing little. Some may fragment before meaningful data is collected. The expectation of diversity must be paired with acceptance of limitation. In reflecting on 3i Atlas, one returns repeatedly to the theme of motion. The galaxy is not a static backdrop, but a dynamic system filled with objects in transit. Stars orbit systems interact debris drifts. Interstellar objects are expressions of this motion made visible only when circumstances align. The human response to such motion is necessarily observational. There is no intervention, no control, only measurement and interpretation. This constraint defines astronomy as a science rooted in patience and inference. Understanding emerges not through manipulation, but through careful listening to what light and motion reveal. As attention gradually shifts to other targets, 3i Atlas recedes from focus. Its data remains stored and revisited, but the object itself moves on. It will leave the solar system unchanged by our presence, carrying no trace of the scrutiny it inspired. What remains is perspective. The discovery underscores how provisional knowledge is, how dependent it is on access and timing. It reinforces the idea that the universe offers glimpses rather than complete revelations. Each glimpse expands understanding without exhausting mystery. In the end, 3 Atlas stands as evidence of connection across distance and time. It demonstrates that the solar system is embedded within a larger galactic context subject to intersections that occur without regard for observation. Studying such an object does not resolve uncertainty. It situates it, placing human curiosity within a moving, evolving cosmos where answers are partial and meaning emerges through accumulation rather than conclusion. As the story of 3i Atlas continues to settle into scientific understanding, its quiet influence becomes clearer. The object no longer commands attention through novelty alone. Instead, it reshapes how astronomers think about what lies between stars and how often the solar system is brushed by material from elsewhere. Its significance grows not from spectacle, but from integration into a broader framework of galactic behaviour. One of the most important shifts prompted by 3i Atlas concerns expectation. For much of modern astronomy, interstellar objects were treated as theoretical byproducts of planetary formation predicted by models but rarely emphasised in observation. Their absence from catalogues created a subtle bias, reinforcing the idea that planetary systems are largely closed environments. Each confirmed visitor erodes that assumption. The solar system appears less like an isolated structure, and more like a participant in a continuous galactic exchange. This exchange operates on timescales and distances far beyond human intuition. Stars form, planets assemble, and debris is scattered outward by gravitational interactions. Over millions of years, that debris becomes detached from its origin, drifting freely through interstellar space. Some fragments encounter other systems, while most pass unnoticed. 3i Atlas represents one such fragment temporarily illuminated by proximity to the Sun. Understanding this process requires rethinking how common such encounters might be. If interstellar objects exist in large numbers, then their absence from earlier records reflects observational limits rather than true scarcity. Modern surveys with increased sensitivity and coverage are beginning to sample a population that has always been present. Each detection refines estimates of density and distribution, gradually transforming speculation into measurement. This realization carries methodological consequences. Astronomers must adapt tools and strategies to objects that do not follow predictable orbits. Rapid response becomes essential. Observation windows are short and delays can mean lost data. The study of 3i Atlas demonstrated the value of preparedness, coordination and flexibility in telescope scheduling. These lessons will shape how future detections are handled. Beyond logistics, 3i Atlas influences theory. Models of planetary system evolution must account not only for what remains bound, but for what is expelled. The mass lost through ejection may rival or exceed the mass retained in smaller bodies. Interstellar objects therefore represent a significant if diffuse component of galactic matter. Ignoring them leaves an incomplete picture. The chemical diversity revealed by 3I Atlas strengthens this argument. Its composition differs markedly from that of solar system comets, reinforcing the idea that formation environments vary widely. Such variation implies that no single system can serve as a universal reference. The Sun's neighbourhood becomes one example among many, not a standard template. This diversity also affects how scientists interpret exoplanetary systems. Observations of distant disks and atmospheres often rely on assumptions drawn from local experience. Interstellar objects provide direct physical samples that can test those assumptions. When discrepancies arise, they prompt revision, broadening the range of plausible outcomes. There is a historical parallel here. Early studies of meteorites transformed understanding of the solar system by providing tangible samples of space material. Interstellar objects extend that transformation beyond local boundaries. They are meteorites on a galactic scale, though most never reach planetary surfaces. Their value lies in proximity rather than impact. At the same time, 3I Atlas underscores the limits of inference. Even with advanced instruments, many properties remain uncertain. Size estimates span ranges. Internal structure is inferred indirectly. Age remains probabilistic rather than definitive. These uncertainties are not failures, but reminders of the complexity inherent in studying distant transient phenomena. Such limitations encourage caution in interpretation. It is tempting to frame each interstellar object as representative of an entire class or origin system. In reality, each carries a unique history shaped by chance encounters and prolonged exposure. Generalization must wait for larger samples. The philosophical implications are subtle but persistent. Objects like 3I Atlas challenge anthropocentric perspectives by emphasizing continuity over uniqueness. The solar system is not a privileged location, but one of many through which debris passes. Human observation is incidental, occurring only when paths intersect briefly. This perspective fosters a sense of proportion. Scientific attention, intense and focused, contrasts sharply with the object's indifference. The universe does not present itself for study. It reveals fragments only when conditions align. Knowledge accumulates through patience rather than command. As 3 Atlas moves outward again, its physical influence on the solar system diminishes. Gravitational effects fade. Activity subsides. Eventually it becomes indistinguishable from countless other dark objects drifting through space. Yet its conceptual influence endures embedded in revised models and expectations. Future detections will build upon this foundation. Each new interstellar object will add context, allowing patterns to emerge where only anomalies once existed. Over time, a population study will replace case studies, transforming how astronomers understand the flow of matter across the galaxy. In retrospect, the importance of 3I Atlas lies less in any single measurement than in the shift it reinforces. It confirms that planetary systems are not isolated outcomes but contributors to a shared galactic environment. Matter circulates, histories overlap, and boundaries remain permeable. This understanding does not diminish the solar system's significance. Instead, it situates it within a larger narrative, one that extends beyond local formation and into galactic evolution. Interstellar objects become messengers of that narrative, carrying information across distances that light alone cannot convey. The study of 3I Atlas therefore marks a quiet expansion of perspective. It does not resolve enduring questions about planetary origins or galactic structure. It reframes them, reminding observers that answers are distributed across space and time, accessible only through fleeting encounters. As the object recedes, what remains is not closure but continuity. The galaxy continues to move. Other objects will follow similar paths. Detection will improve. Understanding will deepen incrementally. And within that ongoing process, 3I Atlas will stand as an early reference point, a moment when interstellar theory became interstellar observation, and when the space between stars revealed itself as an active populated domain, rather than an empty void. As attention gradually shifts from the specifics of 3I Atlas to the wider implications it carries, a deeper question emerges: what does an object like this truly change about how humanity understands the universe? not in terms of spectacle or shock, but in terms of continuity. The significance of 3i Atlas lies in how it quietly connects planetary science, galactic evolution, and the limits of observation into a single narrative. For much of scientific history, astronomy progressed by looking outward and backward in time, inferring structure from light alone. Distant stars, nebulae, and galaxies revealed their secrets indirectly through spectra and motion. Interstellar objects alter that balance. They bring material from distant systems into proximity, allowing direct study rather than inference. This shift is subtle, but profound. It transforms parts of astronomy from purely observational science into a form of sampling. Yet sampling does not imply completeness. The material that reaches us has already been filtered by survival. Only objects large enough, resilient enough, and fortunate enough endure long journeys through interstellar space. Countless others are eroded, fragmented, or vaporized long before encountering another star. 3i Atlas is therefore not a random fragment, but a survivor shaped by endurance as much as origin. This realization reframes how its properties are interpreted. Its unusual chemistry, density, and behavior may not represent typical material from its birth system, but rather material that could survive extreme exposure. Survivorship bias becomes an important consideration. What is observed is not the average but the durable. This principle applies across cosmic scales, shaping what astronomers are able to detect at all. The same applies to timing. The brief window during which 3i Atlas became active and observable was the result of a precise alignment of motion distance and sensitivity. Had it passed slightly farther from the Sun, it might have remained inert and unnoticed. Had modern surveys not been operational, it would have passed silently. Detection therefore reflects coincidence layered atop preparation. This interplay between chance and readiness defines much of astronomy. Discoveries are rarely planned in detail. They occur when instruments are capable and conditions align. 3i Atlas reinforces this pattern. Its appearance did not answer a specific prediction, but validated a broad expectation that had long remained untested. As data from its passage are absorbed into models, its influence becomes less visible but more durable. Orbital statistics refine estimates of interstellar object density. Chemical findings broaden assumptions about volatile distributions. Structural behavior informs simulations of small body resilience. Each contribution is incremental, yet collectively they shift the baseline of understanding. This process highlights an important aspect of scientific progress. Most change occurs not through dramatic overturning of theory, but through quiet adjustment. 3i Atlas did not invalidate existing models of cometary physics or planetary formation. It exposed their boundaries. It showed where assumptions based on solar system examples become insufficient when applied galactically. Such boundary testing is essential. Without it, theories remain locally accurate but globally incomplete. Interstellar objects function as stress tests, revealing how well-established ideas scale beyond familiar environments. In doing so, they encourage development of more general frameworks. There is also an observational humility embedded in this process. Despite advanced instruments and coordinated campaigns, much about 3i Atlas remains uncertain. Internal structure is inferred, not seen. Age is estimated, not measured. Origin is constrained statistically, not traced precisely. These gaps persist not because of oversight, but because of distance and transience. Accepting such limits is part of mature science. Not every question admits a definitive answer. Some can only be narrowed, contextualized, or postponed until new evidence appears. Interstellar objects amplify this reality by offering limited access to systems far removed from direct exploration. From a broader perspective, 3i Atlas reinforces the idea that the galaxy is a dynamic environment of exchange. Matter is not confined to the systems that form it. Over time, gravitational interactions scatter debris, widely creating a diffuse population of travellers. These travellers are neither anomalies nor messengers with intent. They are consequences of ordinary processes operating at large scales. This understanding subtly alters how planetary systems are imagined. Rather than isolated architectures, they become contributors to a shared galactic medium. Material formed in one system may one day pass through another altered but recognizable. Over billions of years, such exchanges accumulate, weaving systems together through motion rather than proximity. The human response to this realization is necessarily reflective. Objects like 3i Atlas underscore the smallness of observational windows and the vastness of the context in which they occur. They remind observers that knowledge arrives in fragments shaped by chance encounters and limited access. As 3 Atlas recedes further into interstellar space, it leaves no physical trace of its passage through the solar system. Its influence exists only in data interpretation and revised expectation. This asymmetry between physical indifference and intellectual impact is characteristic of astronomical discovery. Future interstellar detections will likely feel less singular, but more informative. Patterns will emerge only through accumulation. Each object will contribute a few data points insufficient alone, meaningful together. Over time, the space between stars will become less abstract, populated not just by theory, but by measured entities with varied histories. In that sense, 3i Atlas occupies a transitional place. It belongs to the early phase of interstellar observation, when rarity still dominates attention, and each example reshapes perspective. Later, such objects may be catalogued, routinely studied systematically, and contextualized statistically. For now, its role is quieter. It serves as a reminder that the universe is not arranged for comprehension but for motion. Knowledge follows paths as contingent as the objects it seeks to understand. The study of 3i Atlas does not close a chapter. It opens a longer one, extending outward into a galaxy where material moves freely, histories overlap, and understanding advances through brief silent encounters rather than sustained contact. As the scientific meaning of 3i Atlas continues to settle, its most lasting contribution may be the way it reshapes perspective rather than data. The object does not demand a revision of physical laws. Gravity behaves as expected. Radiation follows known principles. Chemistry obeys established rules. What changes is scale. The encounter forces attention outward, away from local assumptions and toward a galactic frame of reference. For much of planetary science, the solar system served as the primary laboratory. Its comets, asteroids and planets defined categories, behaviours and expectations. Even when exoplanets were discovered, their interpretation often relied on analogies drawn from local examples. Interstellar objects disrupt this habit. They do not fit neatly into established groupings because they were shaped elsewhere, under conditions that may no longer exist near the Sun. 3i Atlas illustrates this clearly. Its chemistry does not align with typical solar system comets. Its activity begins farther from the Sun than expected. Its motion resists common patterns of non-gravitational acceleration. None of these features violate known physics yet. Together they fall outside the comfort zone of familiar models. The object occupies a region of parameter space that had been theorized but rarely tested. This gap between theory and observation is productive. It exposes where understanding is incomplete and where assumptions have quietly hardened into expectations. Interstellar objects act as corrective inputs, preventing models from becoming too locally optimized. They insist on generality rather than convenience. There is also a temporal expansion embedded in this encounter. The likely age of 3i Atlas places it among relics from a period when the galaxy was chemically younger. Studying it extends planetary science backward, in time connecting present-day observation with early galactic conditions. This connection is rare. Most ancient material is locked inside stars or dispersed beyond recovery. Interstellar objects preserve fragments of that history in accessible form. This preservation alters how scientists think about longevity. Small bodies are often treated as ephemeral, easily altered or destroyed. Yet 3i Atlas demonstrates that some can endure extreme environments for billions of years. Survival becomes a defining property shaping which objects remain available for observation. What is studied is not the average outcome, but the resilient remainder. That realization carries interpretive caution. Features observed today may reflect endurance rather than origin. A hardened crust, unusual density, or depleted volatiles may be as much a product of long exposure as of initial formation. Separating these influences requires careful modelling and comparison with future detections. The importance of accumulation becomes clear here. One object offers insight but also ambiguity. Patterns require repetition. As more interstellar objects are observed, scientists will be able to distinguish between traits that recur and those that appear idiosyncratic. Over time, population-level properties will emerge, replacing case studies with statistical frameworks. 3I Atlas therefore functions as both data point and precedent. It demonstrates feasibility. It shows that detection, tracking and analysis of interstellar objects are possible within current technological limits. It also highlights where improvements matter most: early detection, rapid coordination, and multi-wavelength coverage. These lessons influence planning. Future surveys will prioritise sensitivity to fast-moving faint objects. Automated pipelines will be refined to flag unusual trajectories quickly. Observation protocols will emphasise flexibility, allowing telescopes to respond on short notice. Each improvement increases the likelihood that future interstellar visitors will be observed earlier and more thoroughly. Beyond methodology, there is a conceptual shift underway. The space between stars is no longer treated as empty transit, but as a domain containing its own population of objects. These objects are not anomalies or curiosities. They are products of ordinary processes operating across immense scales. Their presence reframes the galaxy as an environment of continuous redistribution rather than isolated systems. This reframing extends to how planetary formation is imagined. Instead of ending neatly within stable architectures, formation becomes a process with outward consequences. Material is lost, scattered, and redistributed. Interstellar objects are evidence of that loss, carrying information about processes that occurred long after formation, but long before observation. From a historical perspective, this mirrors earlier shifts in astronomy. The realization that meteorites originate beyond Earth transformed understanding of planetary material. The recognition that galaxies extend beyond the Milky Way expanded cosmic scale. Interstellar objects represent another such expansion, subtle but consequential. There is also restraint in how their significance is framed. 3I Atlas does not imply intention, communication, or design. It does not suggest purpose beyond physics. Its value lies precisely in its ordinariness within extraordinary scale. It is a fragment, not a signal. A consequence, not a message. This distinction matters. Scientific meaning is grounded in explanation, not implication. Interstellar objects become meaningful through integration into physical models, not through narrative projection. Their stories are written in velocity, composition, and structure, not symbolism. As 3I Atlas fades from observational reach, its influence persists through reinterpretation. Papers will refine estimates. Models will adjust boundaries. New questions will be framed with greater awareness of diversity. The object itself will move on unaffected by analysis, continuing its long transit through the galaxy. In the end, the encounter reinforces a quiet truth. Knowledge advances through brief intersections rather than sustained access. The universe does not offer continuous exposure to its processes. It offers glimpses. Science builds understanding by connecting those glimpses into coherent frameworks, knowing that completeness remains out of reach. 3I Atlas provided such a glimpse. It did not resolve the story of interstellar matter. It confirmed that the story exists unfolding across time and distance far beyond direct observation. That confirmation alone reshapes perspective, placing the solar system within a moving galaxy, where material travels freely, histories overlap, and understanding grows not through certainty, but through repeated fleeting contact. As the passage of 3I Atlas recedes into memory, its deeper meaning emerges not from what was definitively known, but from how it reshaped the questions being asked. Scientific encounters of this kind rarely conclude with closure. Instead, they recalibrate attention-shifting inquiry towards scales and connections that were previously abstract. In that sense, 3I Atlas becomes less an object of study and more a reference point marking a transition in how the galaxy itself is conceptualized. One of the most consequential shifts lies in how motion is understood. The solar system is often imagined as a stable structure, its major bodies locked into enduring patterns. Interstellar objects disrupt that image. They reveal motion as a dominant theme not only within systems but between them. Stars orbit the galactic centre, carrying their planetary debris with them. When systems interact gravitationally, material is exchanged not deliberately but inevitably. 3I Atlas is a record of that exchange. This realization invites a re-evaluation of isolation. Planetary systems are not sealed laboratories. Over long timescales, they lose material and occasionally receive it. The probability of direct interaction remains low, but the cumulative effect across billions of years is non-trivial. Interstellar objects embody this slow circulation, acting as carriers of matter shaped elsewhere. Such circulation complicates notions of origin. When studying a body like 3 Atlas, scientists are not only asking where it formed, but what happened to it afterward. Its current properties reflect layers of influence: initial composition, violent ejection, prolonged exposure to radiation encounters with stars, and eventual activation near the Sun. Each layer modifies the last. Untangling them requires acknowledging that no observation captures a pristine state. This layered history challenges the idea of original conditions. What is observed is always mediated by time. The chemical signatures detected today may differ from those present at formation. Surface structures may obscure internal composition. Even motion reflects cumulative interactions rather than a single event. Interstellar objects therefore resist simple origin stories. They demand narratives that accommodate change. The analytical response to this complexity is comparative. Rather than seeking definitive answers from a single object, astronomers look for patterns across multiple cases. Each interstellar detection contributes constraints narrowing possibilities without eliminating uncertainty. Over time, such constraints become powerful shaping models that can accommodate diversity rather than eliminate it. In this context, 3I Atlas serves as an early anchor point. It joins earlier detections as part of a growing, though still sparse dataset. Differences among these objects are as informative as similarities. Variation in chemistry, activity, and structure signals the range of environments in which small bodies can form. Uniformity would be more surprising than diversity. The encounter also highlights the asymmetry between observation and understanding. Data arrives quickly, but interpretation unfolds slowly. Initial measurements prompt provisional explanations. These are refined, challenged, and revised as additional analysis proceeds. The process is iterative, often extending long after the object itself has moved beyond reach. This temporal mismatch shapes scientific culture. Patience becomes essential. Conclusions are framed cautiously, with explicit acknowledgement of assumptions and limitations. In studying interstellar objects, this restraint is particularly important because the temptation to overinterpret novelty is strong. 3I Atlas resisted such framing by remaining stubbornly complex. There is also an institutional dimension to this shift. The study of interstellar objects encourages collaboration across subfields that are often separate. Planetary scientists, astrophysicists, chemists, and dynamicists contribute complementary perspectives. No single discipline can fully account for an object whose history spans formation, ejection, galactic travel, and stellar encounter. Integration becomes necessary rather than optional. This integration mirrors the object's own journey. Just as 3 Atlas crosses boundaries between systems, its study crosses boundaries between fields. The result is a more holistic view of cosmic processes, one that connects small-scale chemistry with large-scale dynamics. Beyond science, the encounter invites reflection on proportion. Human history unfolds over thousands of years. Recorded science spans centuries. Against that backdrop, the billions of years embodied in 3I Atlas redefine duration. Its existence renders familiar timescales negligible, reminding observers that the universe operates on intervals far beyond lived experience. Such reflection does not diminish human inquiry. It contextualizes it. Knowledge becomes an act of alignment rather than conquest, matching limited access with careful inference. Astronomy, more than most sciences, operates under this constraint. Interstellar objects make that constraint explicit. As attention eventually shifts to new detections, 3I Atlas will remain present in reference lists, models, and assumptions. Its data will be revisited as frameworks evolve. New observations will be interpreted in light of its example, confirming or challenging early conclusions. This persistence underscores an important truth. Scientific significance is not measured by duration of visibility, but by capacity to influence understanding. An object that passes quickly can leave a lasting imprint if it alters perspective. 3I Atlas achieved this by expanding the domain of planetary science beyond the solar system without requiring speculative leaps. In the longer view, interstellar objects may become routine subjects of study. Detection rates will increase. Classifications will stabilize. What is now novel will become expected. When that happens, the early examples will be remembered for their role in opening the field rather than defining it. For now, the lesson remains immediate. The galaxy is not static. It is a system of motion and exchange populated by objects whose paths occasionally intersect ours. These intersections are brief and unremarkable in physical terms, yet profound in interpretive consequence. 3 Atlas did not announce itself with certainty or clarity. It arrived quietly, was measured imperfectly, and departed without pause. What it left behind was not an answer, but an expanded sense of context. That expansion, rather than any single measurement, defines its lasting importance. In acknowledging this, astronomy affirms one of its enduring principles. Understanding grows through accumulation, not finality. Each encounter adds depth, complexity, and humility. Interstellar objects remind observers that the universe reveals itself slowly through fragments, and motion offering just enough insight to widen perspective before returning to silence. As the study of 3I Atlas moves from active observation into long-term analysis, its role within astronomy becomes clearer. It no longer exists primarily as an object to be tracked, but as a reference that reshapes interpretation. The questions it raised now persist independently of its physical presence, embedded in models, discussions, and future expectations. One of the most enduring consequences of 3I Atlas is how it reframes certainty. Prior to confirmed interstellar detections, much of planetary science operated within a closed-system assumption. The solar system was treated as a mostly self-contained archive sufficient for constructing general theories of small body behavior. Interstellar objects disrupt that comfort. They introduce external variables that cannot be calibrated solely from local examples. This disruption is subtle, but profound. It does not overturn existing laws, but it reveals how incomplete local sampling can be. Models built entirely from solar system data may be internally consistent yet globally limited. 3 Atlas forces a recalibration of confidence, reminding researchers that explanatory power weakens when extrapolated beyond familiar boundaries. The object also alters how rarity is interpreted. Rarity in astronomy often reflects detection thresholds rather than true absence. For centuries, meteorites were dismissed as atmospheric phenomena because their extraterrestrial origin could not be confirmed. Interstellar objects occupied a similar conceptual space until technology allowed verification. With multiple detections now confirmed, rarity shifts from assumption to measurable parameter. This shift carries methodological consequences. Astronomers must distinguish between statistical scarcity and observational blindness. The presence of 3I Atlas suggests that the latter played a significant role. If so, then the interstellar medium may be populated by a substantial number of small bodies, invisible until circumstances briefly expose them. That realization changes how future surveys are justified and designed. Searching for interstellar objects is no longer speculative. It becomes an extension of planetary science into galactic space. Resources allocated to detection are no longer pursuing anomalies but sampling a genuine population. Theoretical models must adapt accordingly. Planetary formation theories increasingly emphasize instability migration and ejection. 3I Atlas provides physical confirmation that these processes are not marginal. They are efficient enough to populate interstellar space with long-lived debris. Ejection becomes a central outcome rather than a side effect. This perspective encourages a more dynamic view of planetary systems. Instead of static arrangements frozen after formation, systems are understood as evolving environments, with material constantly redistributed. Over time, what remains bound is only part of the story. What is lost matters equally, even if it travels far from its origin. 3i Atlas also sharpens attention to survivability. Not all ejected material persists. Small fragile objects are destroyed quickly by radiation and collisions. Survivors like 3i Atlas therefore represent a filtered population shaped by endurance. Their properties reflect both formation and survival constraints. This filtering complicates interpretation. A dense structure or unusual chemistry may not indicate common formation conditions but selective persistence. Understanding this distinction requires careful modelling of erosion, radiation processing and thermal evolution. It also requires more examples to establish comparative baselines. The object's long exposure to interstellar space raises additional questions about chemical evolution. Cosmic rays and ultraviolet radiation alter molecular bonds over time, creating complex organic residues. These processes can obscure original signatures while generating new ones. As a result observed, chemistry may encode both ancient formation and prolonged modification. This layered complexity challenges simplistic narratives. Interstellar objects cannot be treated as pristine relics or fully altered debris. They occupy an intermediate state carrying mixed histories. Recognizing this complexity is essential for accurate interpretation. The implications extend beyond small body science. Interstellar objects influence how planetary habitability is considered. While direct biological transfer remains speculative, physical transfer of material is demonstrably real. Molecules synthesized in one system can traverse the galaxy, altered but intact. Over cosmic timescales, such transfer contributes to chemical homogenization and diversity alike. This does not imply intention or design. It reflects physics operating at scale. Gravity scatters, radiation alters, and time preserves what endures. 3 Atlas embodies these processes without narrative embellishment. There is also a cultural dimension to this realization. Astronomy often captures public attention through dramatic imagery or catastrophic framing. Interstellar objects resist such framing. They are quiet, indifferent travelers. Their significance lies in context, not threat. Communicating this subtlety challenges conventional storytelling, but aligns more closely with scientific reality. In this sense, 3i Atlas represents a shift toward mature interpretation. It invites interest grounded in explanation rather than speculation. Its story unfolds through equation spectra and probability distributions, rather than dramatic events. As analysis continues, uncertainties remain central. Size estimates retain margins. Internal structure is inferred, not observed. Age is constrained statistically rather than measured directly. These uncertainties persist not because of oversight, but because of fundamental limits imposed by distance and duration. Accepting such limits is part of scientific discipline. Not every object yields complete information. Knowledge advances through constraint rather than certainty. Interstellar objects highlight this truth by offering limited access to systems that cannot be revisited. The enduring value of 3i Atlas lies in how it reshapes inquiry. It redirects attention from closed systems to open networks, from local norms to galactic diversity, from static categories to dynamic processes. It encourages theories that scale outward rather than inward. In time, additional interstellar detections will dilute the singularity of 3i Atlas. Patterns will emerge, classifications will stabilize. What now feels provisional will become foundational. When that happens, early objects will be remembered not for their anomalies, but for initiating a broader field. Until then, 3i Atlas occupies a transitional role. It marks a moment when interstellar space ceased to be an abstract void and became a domain populated by measurable objects. That transition, more than any specific measurement, defines its significance. The object itself continues onward, unaffected by interpretation. It carries no record of its observation, no imprint of analysis. Its journey persists independently of meaning. The significance assigned to it exists entirely within human understanding. This asymmetry is characteristic of astronomy. The universe does not respond to inquiry. It simply exists. Science advances by aligning observation with theory, accepting incompleteness and expanding context. 3i Atlas offered such expansion. It did not resolve long-standing questions about planetary formation or galactic evolution. It reframed them, embedding local knowledge within a broader moving galaxy. That reframing endures, guiding inquiry long after the object itself has passed beyond reach. By the time attention turns to the wider consequences of 3i Atlas, the object has already fulfilled its most important function. It has forced astronomy to confront scale not only in distance and time, but in probability. Once interstellar objects were theoretical curiosities, now they are empirical facts demanding to be integrated into existing frameworks, rather than treated as exceptions. One of the most significant outcomes is how 3i Atlas reshapes expectations about the Milky Way itself. The galaxy is often described as a collection of stars bound by gravity and embedded in diffuse gas. Small bodies rarely feature in that picture, yet planetary formation models predict that every star system produces vast numbers of minor objects, many of which are expelled. Over billions of years, those losses accumulate. Interstellar space should therefore be populated not sparsely, but continuously by remnants of planetary construction. 3i Atlas provides tangible support for this view. Its existence implies a long history of ejection events across the galaxy. Each ejection represents a system in flux where gravitational interactions reshuffled material violently enough to expel it forever. Seen this way, interstellar objects are not rare accidents. They are the statistical byproduct of planetary systems behaving as physics predicts. This realization shifts how astronomers conceptualize isolation. Solar systems are no longer closed laboratories evolving independently. They are nodes in a galactic exchange, losing material over time and occasionally intercepting debris from elsewhere. While this exchange is passive and uncoordinated, it creates a subtle connectivity across vast distances. That connectivity has implications for chemical evolution. Elements heavier than hydrogen and helium are forged in stars, then dispersed through stellar winds and explosions. Interstellar objects represent a different form of dispersal. They transport complex solids rather than diffuse gas. Their chemistry reflects localized conditions within protoplanetary disks preserved across time. When such objects pass through new systems, they momentarily introduce foreign chemical records. Although their mass contribution is negligible on planetary scales, their informational value is not. Each object carries evidence of conditions that no telescope can otherwise probe directly. This makes interstellar objects uniquely valuable even when they are small and fleeting. 3i Atlas also sharpens awareness of observational bias. Its detection depended on a convergence of timing, trajectory, and technological readiness. Countless similar objects likely passed unnoticed in earlier decades. Even now, detection favours objects with particular velocities, brightness profiles, and trajectories. The sample is incomplete by definition. Recognizing this bias encourages restraint in interpretation. Patterns inferred from a handful of detections may reflect detection filters, rather than intrinsic distributions. Statistical humility becomes essential. The significance of 3i Atlas lies partly in what it warns against premature generalization. At the same time, its discovery motivates improvement. Survey systems are already adapting to identify fast-moving faint targets against crowded stellar backgrounds. Algorithms are refined to detect unusual trajectories. Each improvement increases sensitivity, not only to interstellar objects, but to unexpected phenomena more broadly. In this way, 3i Atlas contributes indirectly to technological evolution. The challenge it posed revealed limitations and prompted innovation. This feedback between discovery and capability is characteristic of astronomy's progress. New objects redefine what instruments must achieve. The object also reframes the language of anomaly. Historically, anomalies in astronomy often triggered speculation beyond available evidence. With interstellar objects, restraint has largely prevailed. While hypotheses vary, most interpretations remain anchored to physics. This reflects a field shaped by prior lessons, cautious in separating evidence from inference. That caution does not diminish curiosity. Instead, it channels it into disciplined exploration. The mystery of 3i Atlas lies not in what it might symbolise, but in how it fits into a broader, incomplete picture. The unknown is acknowledged without being embellished. There is also a philosophical dimension to this restraint. Interstellar objects remind researchers that significance does not require narrative drama. A small, distant body can alter understanding without threatening impact or visible spectacle. Its importance emerges from context, not consequence. This perspective aligns with the deeper ethos of science. Progress often arrives quietly through accumulation rather than revelation. 3i Atlas exemplifies this mode. Its passage produced no immediate transformation. Instead, it adjusted parameters, expanded distributions, and refined assumptions. Over time, such adjustments compound. Models grow more inclusive, simulations incorporate external inputs. Planetary science becomes less parochial, more galactic in scope. This shift does not abandon local study, but situates it within a larger system. As future interstellar detections occur, comparisons will sharpen interpretation. Some objects will resemble 3i Atlas. Others will differ radically. Each difference will test theories, revealing whether current explanations scale or fracture. Diversity, not uniformity, is the expected outcome. In that future context, 3i Atlas will be remembered as an early data point. Its individual properties will matter less than its role in establishing a category. Categories enable pattern recognition, and pattern recognition enables understanding. The object's departure underscores another enduring lesson. Astronomy often studies phenomena that cannot be revisited. Comets fade, stars evolve, objects move beyond detection. Knowledge must therefore be extracted efficiently, often under time pressure, and accepted as provisional. 3i Atlas enforced this discipline. Observation windows were finite, uncertainties remain unresolved, yet the data obtained was sufficient to alter perspective. This balance between limitation and insight defines much of observational science. Ultimately, the legacy of 3i Atlas is not confined to any single measurement. It lies in how it expanded the conceptual boundary of planetary science. It demonstrated that material from distant systems is accessible, analyzable, and informative, even if only briefly. The galaxy is not static scenery surrounding the solar system. It is an active environment populated by objects in motion, shaped by countless interactions over immense spans of time. Interstellar objects make that activity tangible. 3i Atlas passed through without pause or acknowledgement. Its journey continues unaffected by interpretation, yet its brief intersection with observation reshaped understanding. That asymmetry between human meaning and cosmic indifference is not a limitation. It is the foundation of astronomy itself. By the closing phase of its passage, 3i Atlas stands less as an anomaly and more as a reference point. It confirms that interstellar objects are not theoretical curiosities, but measurable participants in galactic circulation. Their arrival reframes the solar system as a porous environment open to material exchange across immense distances and timescales. What once seemed isolated is revealed as connected. The scientific significance of 3i Atlas does not rest on speculation but on constraint. Its chemistry narrows the range of environments in which such bodies can form. Its trajectory tests models of gravitational scattering and long-term survival. Its mass and activity challenge assumptions about how fragile small bodies must be. After billions of years in radiation-filled space, each property removes certainty while sharpening questions. Equally important is what 3i Atlas does not do. It does not violate physical laws. It does not require new forces or hidden mechanisms. Instead, it exposes how incomplete sampling can shape confidence. For decades, comet science relied on objects born around one star. This visitor demonstrates that those conclusions were local, not universal. Historically, science advances through such corrections. New data rarely overturns fundamentals, but it often widens context. Interstellar objects expand the frame from planetary to galactic, from episodic encounters to continuous exchange. They suggest that planetary systems lose as much material as they keep, and that this loss becomes part of a shared cosmic inventory. As 3i Atlas departs, it leaves behind more than measurements. it leaves a methodological shift. Future discoveries will be interpreted with greater caution, broader models, and less reliance on familiar templates. In that sense, its brief appearance produces a lasting change, not an answer, but a recalibrated way of asking. Traveller. As this story settles into silence, what remains is not an answer, but a feeling. A sense that we have brushed against something vast, ancient, and briefly illuminated by human curiosity. Thisna Atlas drifts onward now unchanged by our attention, yet forever woven into our understanding of the cosmos. What we witnessed together was not spectacle but connection, a reminder that the universe is not distant or indifferent, but quietly expressive. It speaks in trajectories in chemistry and faint light gathered patiently across unimaginable distances. To listen is an act of humility. To understand even partially is a privilege. We are small beneath these scales of time and space, but not insignificant. Each observation matters, each question refines the story. Through instruments like James Webb, we are learning that the galaxy is alive with motion exchange and memory. Worlds are not isolated, histories overlap. Even the silence carries meaning, and so the mystery continues. Somewhere beyond sight, other travellers move between stars. Other fragments wait for light to reveal them. The universe is still unfolding, still whispering long after this moment fades. If this story found you tonight, let it rest with you. Let wonder soften the edges of thought. Let time feel wide again. Rest well, traveller. The universe will keep watch.